Welcome my friends, welcome to my next lecture. Now this lecture, as you see, I want to, or in fact I should talk about what is called surface integrals. So in my last lecture I talked about what is called line integrals. So I introduced the notions of contour, smooth curve, and then I introduced the concept of what is called scalar line integral, then vector line integral, right. So now this lecture I will talk about what is called surface integrals, right. Surface integrals means what? I have to introduce first what do I mean by surfaces. In fact you people are familiar with, in fact in the beginning of my lectures, couple of lectures I introduced these notions. So again I will recall that. So first I will start with the definition of surfaces, then I will introduce the notion of smooth surfaces, what is called oriented surface, then I will define the notions of what is called scalar surface integral and then vector surface integral and couple of properties. So that's the plan for next couple of lectures to talk about surface integral, and then you will see when I will talk about in my last two concepts I should say, that is called what is called Stokes theorem, Green's theorem or divergence theorem. So I need these notions of what is called like line integral or surface integrals. Once I have that notions of line integral and surface integral, then I can talk about what is called Stokes theorem, Green's theorem and divergence theorem. Okay, so for that, so now coming 1 or 2 lectures or maybe 3 lectures, I just focus on the concept called surface integrals, and once I have the notions of, first I will introduce the notions of surfaces and then I will talk about what is called scalar surface integral and then vector surface integral along with some properties. Okay, so these are the learning outcome for coming 1 or 2 or maybe 3 lectures. So first I will start with what is called smooth surface, the definition of smooth surfaces, and then I will talk about finding normal vectors to the smooth surfaces. Okay, then as I said, I talked about what is called, I will introduce the notions of what is called scalar surface integral over smooth surfaces, and then I will talk about the notions of oriented smooth surfaces. That means if I have a smooth surfaces, then there is a notion called orientation. Then of course one example I will talk about examples of non-orientable surfaces, that means that Mobius strip actually, that is non-orientable surface, and then I'll at the end I will talk about what is called vector surface integral and then couple of examples and some properties I will discuss. Okay. As I said, so let's recall the definitions of surfaces in, again I restrict myself in 3-dimensional Euclidean space. Okay. Okay, so that's the heading, it's the surfaces in R3. That means I want to talk about surface. Of course you can define surfaces in Rn as well, so but at least for R3 you can have more what is called visualizations, because you can at least see pictorially what is going on. So that is why I restrict myself in the 3-dimensional Euclidean spaces. Okay, so that is why I have written that surfaces in R3. So what is the definitions of surfaces in R3? The definition is that a surface S, that is the notation. So our surface S may be thought of the graph of a continuous functions from a rectangular region or a simple region R in the plane to the space R3. So that means a surface S in R3, that means I can think about it is a graph of a continuous function. And what sort of continuous functions? So continuous functions from some domain subset of R2. What sort of domains? It is either rectangular region or simple region in the plane, that means in R2, and it taking values in 3-dimensional Euclidean space. So that means the graph of a continuous function whose domain is in rectangular region or some nice simple region R in R2 and the values is in R3, then the graph of this continuous function you can think about as a surface. Okay, for example, let's see one example. So that means you can think about like, so this is my surface, so you can think about it's a kind of map R. Okay, so I think these are same, so it's a map, say let it be psi, it's a map from some region R which is subset of R2 to R3. So graph of, so S is nothing but graph of this one is called the surfaces. Okay, let's see one example, then it will be more clear. So for example, if I take this kind of functions, G function, G is a map from your region R to R3, and what is that map? So that means what I am saying is that suppose G is a map from where to where? It's a map from R which is subset of R2 to what is called R. That means it's a scalar field. Okay, so that means G of xy that I am denoting as Z which is in R, then that will give you a surface. What is that surface? I will say that take S which is nothing but all those x, y, z in R3 such that x comma y is in R, that means it is a subset of R2, and z which is nothing but g of xy. Okay. So that means, so that will give you a kind of example of surface. What we have? So if z is equal to g of xy, where xy is running over your region R in R2, then if I consider this collection S, which is nothing but all those point x, y, z in R3, where x comma y are coming from R, the region R in R2, and z, which is nothing but g of xy, where g is a map from your region R subset of R2 to R. That means it's a scalar field, right? So that means xy belongs to R and z is equal to g comma xy. So that you can think about as a surface. Okay. So now another example. So this is, you can think about as a like continuous function, graph of a continuous functions. Like what is that? It says that, okay, so consider the region R, which is xy is in R2. So but it is a special type of region where x running from 0 to 1 and y running from 0 to 1 minus x. That means you can see what sort of region. So this is the region, right? So y is equal to 1 minus x, that means x plus y is equal to 1. So that is the straight line, okay. And so this is 0 1, this is x, and y running between 0 to 1 minus x, that means y should be there. So that means this is the region I am talking about, okay. So this is the region R, that is the region R. And what is my surface? So my surface z, which is exactly equal to 1 minus x minus y, xy belongs to R, this is the surface. That means what is my function g? So my function g, which is a map from R2 to R, and what is that map? G of xy, that I am saying, which is nothing but 1 minus x minus y. That's the functions, okay. So if that is the case, then the surface is nothing but x comma y comma z. So what is your surface? Surface is nothing but x comma y comma z. Z is nothing but 1 minus x minus y, okay, where x comma y belongs to R. So that is the surfaces, okay. So that is another example. Look, another example I have given. A surface S can be thought of as the level surfaces of the function g of x, y, z is equal to 0. So suppose you have a function g, say from R3 to R, so it's a kind of scalar field, okay. Then the corresponding level surfaces you can also think about as a surface. So what does that mean? That means define the set S, which is the collection of all those x, y, z is in R3 such that g of x comma y comma z is equal to 0, or say another example, x, y, z is in R3 such that g of x comma y comma z is equal to 0, and what is the g of x comma y comma z function? This is nothing but x square plus y square plus z square minus 1. So this is a particular function g. So I am talking about the g of x, y, z, which is nothing but x square plus y square plus z square minus 1. So this is the functions. If this is the case, then this is the corresponding level surfaces of the function g of x, y, z is equal to 0. So therefore the surface S can be thought of as a level surfaces of the function g x, y, z is equal to 0, where g is a function and it's a scalar field, okay. So these are the examples of surfaces, okay. Whatever I said, I again just pointed out in a similar kind of concepts. So what is the first one? So locus of a point moving in a space with 2 degrees of freedom, that you can think about as a surface. Number 2, same already discussed, level curve of a scalar field. So that means earlier one like g function, g is a scalar field, is a map from some domain D subset of R3 to R, and then g of x, y, z is equal to 0, it will give you the level surface is nothing but the surfaces, same thing. So level curve, in fact we can say that level surface of a scalar field f from R3 to R. For example, x square plus y square plus z square is equal to c, or z is equal to x square plus y square, etc. Okay. Number 3, sometimes surfaces can be described as x comma y comma z, x y running over the domain in R2, okay, and what is my z? Z is a function of x comma y. So that's as I said, so this is the one, no? So this is the one, okay. So x comma y comma z, where x y running over the region R and z is equal to g of x y, okay. So this is the one. This is called the explicit representations of the surfaces. Another one 4. So now you can think about, once I have the explicit representations, that means x comma y comma z, where z is a function of x comma y, where f is a map from D subset of R2 to R, then this is called the explicit representation. For example, the unit sphere is a union of 2 such explicit representation. What about the first one? So first one is x comma y, where x square plus y square lesser equal to 1, that means 2 dimensional, it is a unit interior region of the circle. So that means it is a circle inside including the boundary, it is the region. So this is x comma y, and what is your z? Z is nothing but square root of 1 minus x square minus y square. This is union x comma y, and this is z, which is nothing but minus of this one. So what is the first one? First one will give you the upper hemisphere, right, and second one will give the lower hemisphere. Okay, so that's what the meaning of this unit sphere is, a union of two such. So this one it will give the upper. So because here z is positive, right, this is upper hemisphere, this is the lower hemisphere. Okay, so union of two such explicit representation will give you the what is called unit sphere. Okay, so now once I have the surfaces, then there is a parametric representations of the surfaces, that is called parametric. In fact, when I will talk about the what is called scalar surface integral or vector surfaces integral, so that means if I have a surface started with, then I will start with a parametric representations, and then I will define, you see what is the definition of scalar surface integral or vector surfaces integral. So that is a parametric representation of a surface is needed to talk about what is called scalar surface integral and vector surface integral. So that exactly I have written. A surfaces may also be described as, of course I am talking about surfaces in R3, so that means the each of the variable x, y, z in R3 can be written as a functions of u and v, where u, v in varies over the two-dimensional plane. So that means this x is equal to capital X of u v, y is equal to capital Y of u v, z is equal to capital Z of u v, where u v is in D, where D is a connected, look what is the definition, u v running over D subset of R2, D is a connected subset in the u v plane. For example, plane like region, circle, rectangle, so these are the region. So if I have a circle, if I have a rectangle, if this is the region in the UV plane, u comma v varies, and if I write my small x, small y and small z as a function of uv, then this is called the parametric representation of your surfaces in R3. Okay. Well, I will talk about example, then it will be more clear. So that's exactly I have written in terms of definitions. So R continuous functions capital R from D subset of R2, where D is very nice domain, to R3 is called a parametric surfaces in R3. Okay. So this is, in fact, once I have the continuous functions capital R, this is the parametrizations of the surfaces actually. Okay, so our continuous functions capital R from a set D subset of R2 to R3, or domain D or subset of R2 is very nice domain. That means it is actually either circular region or rectangular region. Okay, D subset of R2 to R3 is called the parametric surface in R3, and if I take the image, that means image of R of your domain D, then R of D, if I look at the image and if I say that this is the image S, this is sometimes called the what is called geometric surfaces in R3. So that is give you the geometry in the R3. Okay. If the surface, look, if the surface has an explicit representation given by the continuous function z is equal to f comma xy, so that explicitly given, right. So that means, so I have xy which is running over some domain D subset of R2, and I can have a explicit expression of z in terms of xy, right. That means z is equal to f of x comma y. Then what is my R? R will have x comma y comma z, it's a map from R2 to R3. So what is my first component? Of course it is x, second component y, and what is the third component z, which is nothing but f of x comma y. So that means I can have Rxy, which is x, y, f of xy, it's a parametric representation. Okay, so that's very nice. So that means if I have a surface, if it is an explicit representation given by a continuous function, so that's kind of things, no? So this is called the explicit representation. That means I will have x comma y comma z, where z can be obtained as a function of x comma y, where f is a map from D subset of R2 to R, it's a scalar field. If I have that kind of representation, this representation is called the explicit representation. So what I am saying is that if the surface has an explicit representation, that means I have a functions f from some domain D subset of R2 to R, such that x comma y and z I can write in terms of f of xy, then your parametrizations are, which is a map from D subset of R2 to R3. And how this parametrization works? So R of x comma y, which is nothing but x comma y comma z, z is there, and z I can have the explicit expression in terms of x and y. So that means this is nothing but f of x comma y. Okay, because the explicit expression of the surface is given. So therefore this is nothing but the what is called the parametrizations of my surfaces in R3. That's exactly. So this is called the parametric representations. So therefore if the surface has an explicit representations given by the continuous function z is equal to f of xy, then I can have the parametric representation of the surfaces. That means I have the parametrizations capital R, which is defined this way. So xy as it is, x times I cap, y times j cap, okay, and z should be replaced by function of xy, that means small f of xy times k cap. Okay. So, therefore, if I have a explicit representation of my surface, then I can have the parametric representations, and that is very nice. So, r of x comma y is nothing but x comma y comma f of xy, small f of xy. Okay. So, that small f is nothing but explicit representation of my surface. Okay, so this is another parametric representations of a sphere of radius a. I think some of you are familiar with. If I have a sphere, what is the corresponding spherical coordinate, if you remember? So you have a Cartesian coordinate, right? X square plus y square plus z square is equal to 1, but you can have the representations in terms of what is called spherical coordinate. I already discussed in my previous lectures, but again I should recall it. Okay, look, so if we take the spherical coordinates, then once I have the spherical coordinates, then there is a relations with the spherical coordinates like phi, theta and r in terms of Cartesian coordinate x comma y comma z. And what is that? This capital X or small x, that is the Cartesian coordinate, I can write in terms of theta and phi. And what is that? This is capital X of theta comma phi I am writing. And what is the relations between spherical coordinate and Cartesian coordinate? So Cartesian coordinate small x can be written as a sin phi cosine theta, y is nothing but a sin phi sin theta, and z is equal to a cos phi, because I am starting with a sphere of radius a. So sphere of radius a is fixed. Therefore, the right hand side is a function of phi and theta. This is a function of phi and theta. This is also a function of phi and theta, and that I am written as capital X of theta comma phi, capital Y of theta comma phi, and capital Z of theta comma phi. But you should be careful here. Phi and theta varies in some intervals. Phi running from 0 to pi, theta running from 0 to 2 pi. That I know. The relations between Cartesian coordinate and spherical coordinates. So if I write my Cartesian coordinate x, y, z in terms of spherical coordinate, and which I denote it as capital X of theta comma phi, capital Y of theta comma phi, and capital Z of theta comma phi, then this gives a parametric representation of my sphere. Then what is my parametric form? Capital R. So capital R acting on theta comma phi or phi comma theta, which is nothing but x is nothing but a sin phi cosine theta, y is a sin phi sin theta, and z is a cos phi. So that means you can write r phi comma theta, which is subset of R2, right? What is the subset? So it's a map from 0 pi, phi is running by 0, cross 0 to 2 pi, which is subset of R2 to R3. That means it is nothing but a sin phi cosine theta, a sin phi sin theta, and then a cosine phi, which is subset of, which is element in R3. So this is the parametric form of your sphere. So if I know the connections between spherical coordinates and Cartesian coordinates, then I can have the parametric, what is called, representation of my sphere in terms of phi and theta, which is r of phi of theta, which is nothing but this, where phi runs from 0 to pi and theta runs from 0 to 2 pi. Okay. So this is the parametric representation of my sphere of radius a. Now similarly, I can think about the parametric representations of a cone. Okay. So what is the definition of cone? So definition of cone means what? So z exactly equal to square root of x square plus y square, and z running from 0 to 1. So that will give you a cone. Okay. So that means if you have the picture like that, it is like right. So this is x, this is y, and this is z. Okay. So at z is equal to 0, it's a point. Oh sorry, it is not the case actually, because if I put z is equal to 0, that means here it should be a point, right? So I mean it is the opposite one, I should say. It is the opposite one, right? So that means, so I have this. So this is x, this is y, this is z. So z is equal to 1, it will be a circle. So that means it should be like that. This is z is equal to 1. Okay. So this is the cone. So this is the cone. So now question is, what is the parametric representation of a cone? So this is my cone in terms of Cartesian coordinates. Now you know there is a concept called cylindrical coordinates, I already discussed. So here cylindrical coordinates provide everything we need. And what is the relation between cylindrical coordinates and the Cartesian coordinates? If you remember, I have discussed this kind of observations, I think in my lectures. Maybe I forgot, maybe I think couple of lectures before, I think maybe when I talked about what is called double integral and in triple integral. Yes, if I remember correctly, when I talked about triple integral, and there I have introduced the notions of what is called like change of variable. When I talked about change of variable, like if I have some problem in the Cartesian coordinate system, I want to change it to what is called spherical coordinate system or cylindrical coordinate system, then I need to know what is the relations between Cartesians with spherical, Cartesians with cylindrical. There I have discussed the notions of spherical coordinate system, cylindrical coordinate system. So if I have those coordinate system, like here the cylindrical coordinate system, you know it's provided everything what we need. That means I can write my x in terms of r and theta, and what is this? X of r theta, which is nothing but r cosine theta, y is a function of r and theta, which is r sin theta, and z is a function of r and theta, which is nothing but r. Okay, so therefore each coordinate x, y, z can be written as a function of r and theta, and where r running from 0 to 1, theta running from 0 to 2 pi. So therefore the corresponding required parameterization is capital R, okay, which is a map from 0 1 cross 0 to 2 pi, which is subset of R2 to R3. And what is that? That means r comma theta goes to r cosine theta, r sin theta, comma r. So this is the corresponding parametric form of this cone. That exactly I have written. So the required parameterization is capital R of small r comma theta, whose first component is r cosine theta, second component is r sin theta, and third component is r, where r running from 0 to 1 and theta running from 0 to 2 pi. Okay. So this is the corresponding parametric representations of my surfaces, which is nothing but the cone. Earlier one, it is the parametric representation of a sphere. Okay. So if I know the relation between Cartesian coordinate and spherical coordinate, so I can have the parametric representation of my sphere, and if I have the cylindrical coordinate system and relations between cylindrical coordinate system and Cartesian coordinate system, then I have the notions of what is called parametric representation of this cone, which is nothing but this one. Okay, so now at least you have some idea what is the meaning of surfaces, right? So various way you can think about that. Okay, it's either it is a graph of the continuous functions or the explicit representation. That means if I have a nice function small f from some domain subset of R2 to R given by z is equal to f of x comma y, explicit representation, then you will have the corresponding surfaces, and then you can have the what is called corresponding parametrizations. Parametrizations I have talked about. This is the parametrizations. So continuous functions are from domain D subset of R2 to R3 is called the parametric surfaces, and the image is called the geometric surfaces. I have discussed the notions of what is called surfaces and couple of examples and parametric representation I have discussed. Now I come to the concept what is called smooth surfaces in R3. So you need surfaces which satisfy some properties, then I will say those surfaces become say smooth surfaces in R3. Okay. So okay, look. So what is the definitions of smooth surfaces in R3? So I have to start with a region R in R2 satisfying the following properties. What are the properties? So that means it is not the arbitrary region in R2, it has some properties. First of all, the region should be convex and bounded region in R2, or R is vertically and horizontally simple region. So that means it should be convex, it should be bounded, and vertically and horizontally simple region. Now what is vertically and horizontally simple region? Again, when I talked about double integral, I have discussed those kind of simple region. If you remember, like vertically, what is that vertical region? That means if you remember, yeah, so I think it should be this. That means it is say some curve, right, g1x, and this is g2x. So that means the region bounded by this x equal to a and x is equal to, this is x is equal to a, this is x is equal to b, but y is bounded by the curve y is equal to g1x and g2x. So this is g2x. So if this is the region, then it is called vertically simple. That means you can parallelly, if I go vertically directions, then I can cover the full region. This is, so this is called vertically, if you remember. And what about the horizontally? This is called vertically. And what is horizontally, if you remember? Horizontally means what? Y should be fixed. That means you have this y fixed, but x should be bounded by some curve. So that means I think, yeah. So this x should be g1 of y, and this is x should be g2 of y. That means horizontally if I move, then I can cover the whole region. So this is the region actually is called what is called horizontally simple, and this is called the vertically simple region. So therefore I need my region in R2 which is kind of very nice region. That means it is convex, it is bounded either vertically and or horizontally simple region. So that means if I start with those kind of nice domain which is convex, bounded either horizontally or vertically simple domain, then if I start with the functions, let phi be a functions from your domain R, which is very nice, I have just discussed, it should satisfy these two properties to R3 such that phi of uv is nothing but x uv, y uv and z uv. That means it's a map from R to R3 whose first component, so that means you can write u comma b, which is x uv, y uv and z uv. Okay. So, let phi be a function whose components are like that and it satisfies some of the properties. What are the properties? Phi should be continuously differentiable in R. So, that means phi should be differentiable, that means derivative should exist and derivative is continuous, that is the meaning of continuously differentiable. That means it is a member in C1 of R. Okay. So, that means phi is an element in C1 of R, that means continuously differentiable, number 1. What is number 2? Phi should be injective or 1 1 except possibly on the boundary. So, if you remove the boundary points, means interior of R, interior of my region R, it should be injective or 1 1. This is number 2. And number 3, for each point P in R, the normal vector phi up and cross phi bp, it should be non-zero. That means existence of what is called the vector, normal vector should be non-zero. That means the normal vector should exist non-trivially. So, now what is this phi up and phi vp? So, phi up, if you remember, these are notations, right? Phi up means what? This is nothing but del phi del u at the point P. And what is del phi del u? Which is nothing but this component. That means you have del x del u, del y del u, okay, and del z del u, right. So, this is the vector, okay. So, that you have to at P. Okay. So, that means this is a vector phi up, that means it is del phi del x del u at the point P, del y del u at the point P and del z del u at the point P. So, this is a vector. Similarly, phi v. So, phi v p, which is nothing but del phi del v at the point P, which is nothing but del x del v at the point P, comma del y del v at the point P, comma del z del v at the point P. Okay. So, therefore, this is my phi up, this is my phi bp, and if I take the cross product, this is the normal vector and it should be non-zero vector. Okay. So, if I have a nice region R in R2 which is convex, bounded, horizontally simple or vertically simple, if I have a map phi from my region R to R3 whose components are x, y, z, x is a function of ub, y is a function of ub and z is a function of ub, and if it satisfies the following three properties, what? Phi should be C1 of R, that means it is continuously differentiable. Phi should be injective in the interior region R, not in the boundary, I do not care about boundary, and for each point in my region R, the normal vector which is phi up cross phi bp, it should be non-zero. Okay. If that is the case, then if I take the image, so what is my image? That is the geometric surfaces, right. So, that means this is the parametrizations, phi is the parametrizations, right, small phi is the parametrizations. So, then if I take the image S, which is nothing but phi of R, is called the smooth surfaces is R3 with parametrizations phi defined over the region R, or I will say that it is simply called parametrized smooth surface. Okay. So, now I think it is clear what is the definition of smooth surface, in fact parameterized smooth surface. So, first you have to start with a what is called nice domain in R2, that I am denoting as R. This is my notations R, and so and R, what should be R your? That R should be very nice, that means it should be convex, it should be bounded, it is either horizontal or vertical simple domain, that is my R in R2. And now I am starting with the functions phi from my domain, nice domain R subset of R2 to R3 whose first component is x uv, second component is y uv and z component is z of uv. So, phi is a map from R subset of R2 to R3, phi of u comma b is nothing but x uv, y uv, z uv, and if phi satisfies the following three properties. What are the properties? Phi should be C1 of R, that means it is continuously differentiable, number 1. Number 2, phi should be injective in the interior region R, so that means I do not care about the boundary of R, but as long as it is in the interior it should be injective or 1 1. And third one is that for each point P, if I take any point P in R, then the corresponding normal vector, that means phi up cross phi bp, it should be a non-zero vector. If that is the case, then if I take the image of my phi of the region R, if I denote it as S is equal to phi of R, then it is called the smooth surface in R3 with parametrizations is phi. and this is sometimes I'll call this simply, or sometimes I will say that this is parametrized smooth surface. So it is a smooth surface, and of course parametrization is small phi. Okay, so this is the definition of smooth surfaces. Okay, so couple of examples of smooth surfaces I have given. For example, if I consider the sphere, so it is a surface in R3, right? And what is the parametrization? I have just discussed the parametrizations of sphere, like there is a relation between spherical coordinate system. Now it's a sphere of radius 1, so therefore the small a part exactly equal to 1. Look at here. So you see, so this is a parametric representation of sphere. So that means here a is equal to 1. That means sin phi cosine theta, sin phi sin theta, a cos phi, right? That's what it should be. You see, look. So I have a functions phi. Of course, this is my parameter. So there I have a parameter phi and psi. So here actually I am just changing the notations. So just to make uniform with the earlier one phi, so I am just replacing that earlier one u by small u and small v. So small u runs over 0 to pi, small v runs over 0 to 2 pi, 2 R3 because this is a very nice domain, okay, it's a square region. And what is the parametric representation? Phi of ub. So this is nothing but sin u cos b, sin u sin b, and cos u, because here a is equal to 1, u runs from 0 to pi and v runs from 0 to 2 pi. So this is the corresponding parametric, or of course this is a smooth surface, means the sphere is a smooth surface, and this is the corresponding parametric representations. Okay. So this is one example of smooth surfaces, because look at the component. So these are the component, na? So what about the phi is in C1 or not? So of course it is each of the component is a combination of sine function and cosine functions, and each of them are C1 functions, right? So therefore, since it is differentiable, derivative is continuous, this is also differentiable, derivative is continuous, this is differentiable, derivative is continuous. So therefore you can think about that phi is a C1 map. So that means it is 1 times continuously differentiable, number 1. Number 2, if I think about the interior region, that means if I omit the boundary points in the interior region, of course you can check, I didn't prove everything, so it is actually 1 1 or injective. And of course the third part is that if I take any point in my region, that means the corresponding phi u at that point cross phi v at that point should be a non-zero vector. Again, I didn't calculate it, but anyway, if you calculate it, you will get it is a non-zero vector. In fact, this one maybe I have done it, let's see. Yes, so one part I have done it, okay, anyway. So that means it is a smooth surfaces, but provided couple of things you have to verify. What are the things? That means this is the part you have to verify, right? So except possibly on the boundary, that means the region it should be 1 1, that you have to check, and for each point this should be a non-zero vector. But you can do that because you have the explicit expression of x, y and z. Okay, you have to just use the formula, and I have to just compute it, and you have to just verify it. Okay, so kindly verify this one, that whether phi is 1 1 in the region open 0 pi cross open 0 to 2 pi, in that region whether it is 1 1, and you have to show that if I take any point p in my region 0 to pi cross 0 to 2 pi, the corresponding vector phi up cross phi bp, it's also non-zero vector. Phi up you can easily calculate because these are the component function, you can easily calculate, and similarly phi bp you can calculate. Then you take the cross product, let's see whether it is a non-zero vector or not. You can see, you can easily get it. So therefore this portion I am just left as an exercise, you complete it. Okay, so that is the first example of smooth surface. Second one is that hemisphere. Okay, that means I have the sphere, I am considering the only the upper one. That means here z is equal to 0. And what is the parameterization? So of course you will see it is parameterized by phi r to R3. What is my R? R is the kind of domain or region in R2, which is nothing but the circle x square plus y square. This is the kind of things. X runs over -1 to 1, and y should run over, again see what, now you can see this is actually vertically simple region. Okay, g1 x to g1. So this is a vertically simple region, right? And what is my parameterization? Phi of xy is nothing but x comma y, and z is replaced by square root of 1 minus x square minus y square. So that is the explicit representations of my hemisphere that I already discussed. So this is the corresponding parameterizations, and my region R here is vertically simple. That means x running from -1 to 1, however y running from g1x to g2x. That means vertically simple. So R is vertically simple. Your phi is, this is the component function. Again the component functions are very nice. You can take the derivative, you can check that it is C1. Of course the part that it is injective in the open region, and if I take any point in the region R, the corresponding vector phi up and phi bp. Here actually phi u means what? Phi xp and phi yp. That cross product should be non-zero. Also you can check it, it should be non-zero. Okay. So again these are the calculations. I am just left as an exercise. You complete it, you will get that this is nothing but the case, and therefore it is a example of smooth surfaces. That is second one. What is the third one? Third one, again it is the cone, that means z is equal to square root of x square plus y square, z running from 0 to 1. And what is the parametrization? I have just discussed the parametrization in terms of cylindrical coordinate system. So this is the phi of r theta, which is x component is r cosine theta, y is r sine theta, z is equal to r. So it is very nice. So therefore it is a function of r theta, it is a function of r theta, it is a function of r theta. Again it is C1, because it's a very combinations of sine cosine functions and the functions r. Okay, so it is C1. Again you have to check in the, if r running from open 0 to 1 and theta running from open 0 to 2 pi, it should be injective. And of course if I take any point from this region 0 1 cross 0 to 2 pi, the corresponding phi r at the point P and phi theta at the point P, that cross product vector, that should be a non-zero vector. Again you can check it, you will get it. It's very simple because all the component function is given, so you can do that. So that means this, what is this? This is x of r theta, right? So what is x of r theta? This is r cosine theta. What is y of r theta? That is nothing but r sine theta. And what is z of r theta? This is nothing but r. So this is a nice function, this is a nice function, this is a nice function. You just do the calculation, that's it. So of course C1 part is perfectly alright, that is you don't have to do anything. The only second and third part you have to compute. That means you have to check it is injective or 1 1, and you have to check that at each point in R this should be non. Again you can calculate explicitly, now you have all the expression in your hand, you just calculate. So here what will you have? Phi r, then phi rp cross phi theta p, you have to calculate, and you can calculate it very easily. And injectivity you can check it, I think you will get it. So therefore if I have this, these are the kind of surfaces and it satisfies all the properties in last slides. So therefore these are the few examples of smooth surfaces. So now there is a, as I said, how to find the normal vector given a smooth surface S. So let S be a smooth surface in R3 which is parametrized. So parametrization you know. So that means it should be a functions phi from some nice domain R subset of R2 whose component are x, y and z, it's a functions, and it's a smooth surface. So smooth surface means of course it is in C1 of R, it is injective in the interior region. If I take any point P is in R, the corresponding phi UP and cross phi VP is a non-zero vector, all everything's are there. So here I have written, so this is the corresponding parametrizations where my R region, R is simple convex region in R2. Then you can easily calculate your phi U at any point U comma B, which is nothing but del x del U, del y del U and del z del U, that is the corresponding phi U. What is my phi V? Again you know the component x, y, z, that means this is del x del V, del y del V, del z del V at the point U comma B. You have phi U at the point, phi b at the point. So that means you have the concept of phi u at the point u comma v, which is nothing but this one. You have a phi v. What is phi u? Del phi del u, I should write. So this is same as del phi del u at the point u comma v, and this is u comma v, that means this is del phi del v at the point u comma v. Okay, then you have to take the cross product, right, if you remember. So if I take the cross product phi u cross phi b, and this is the formula you know in terms of determinant formula, right. So this first row should be I j k and the corresponding component of phi u and phi b. So that means this is the component of phi u and this is the component of phi b. So if I get that one, then that will give you the vector phi u cross phi b. Then I am defining the unit normal vector n cap to the surface S is given by unit normal vector n cap. So that means phi u cross phi b will be there, and you have to divide it by, because I am unit vector I am talking about, it divided by norm, either mod or norm, it doesn't matter. And plus minus, of course, plus means actually outer direction and minus means inward direction, that's the meaning of plus minus. So therefore if I have a smooth surface with my parametrizations phi, then I have the notions of phi u and phi b. What you do, you take the cross product phi u cross phi b, this is a vector, this will give you a vector. Then I am defining the unit normal vector n cap to my surfaces S by this formula. So which is nothing but n cap, which is nothing but phi u cross phi b divided by norm phi u cross norm phi b. Okay, so norm of, I should say the norm of or mod of phi u cross phi b. So if I have a smooth surface S with my parametrizations phi, then what is the normal vector? So this is the definition of normal vector. Unit normal vector n cap, which is nothing but phi u cross phi b divided by modulus of phi u cross phi b. Okay, so it's very easy. So if I know my parametrizations phi, that means I know my component x, y, z, that means I know my vector phi u, I know my vector phi b, take the cross product and then normalize it with a plus minus sign, will give you the what is called normal vector to my smooth surfaces S. Okay, so I think, yeah, so that's okay. So that means if I have a surface, smooth surface with my parameterizations phi, which components are x, y, z, then this is the corresponding formula for what is called unit normal vector. Now, what is this one? It says that I have a smooth surface, again I want to find a normal, but this time I have a what is called explicit formula for my surfaces. So, suppose the surface S is defined by the equation, that means the explicit representation of my surfaces. That means I have a nice function small g such that z is equal to g comma xy, where xy running over r, and r is horizontally or vertically simple convex region in the xy plane R2. So, what is my surface in this case? My surface is nothing but x comma y comma z in R3, xy should run over r, and z is equal to g comma g of xy. That is explicit representation. If you remember, I already discussed explicit form, right? What is that? Yeah. So, you see, if the surface, so look, this is the explicit representation. Yeah. So, if the surface has an explicit representation given by the continuous function z is equal to f x y, so this is the corresponding parameterizations, right? X comma y comma f of x y. So, this is one, another this you see, this is the explicit one. Sometimes surfaces can be described by x comma y comma z, where z is equal to f of x y, where f is very nice, d is nice domain, then this is called the explicit representation. Now, if I have explicit representation, then I can have the corresponding parametric representation, right? That is exactly I am doing. So, this is my surface, right. So, therefore, my surface is explicit representation is given, that means x comma y comma z, while x y is running over r, a nice region in R2, and z is equal to small g of x y, where g is a function from my domain R subset of R2 to R. It is a very scalar field. Okay. Now, what we have to do is just once I have the explicit representation of my surface, then what will be the corresponding parametric representations, right. So, that you know. So, what is my parametric representation? Phi. So, phi of x y, you can write it, this is nothing but x comma y comma z, and z is given by explicit representation small g, right. So, this is the corresponding parametric representations. Now, what is this function? This is my functions, nice function, first component x, second component y, third component g of x y. Then you do the formula, same thing. Okay. So, what you have to do? Look, so this is the explicit representation of surfaces given. Now, rewrite it in parametric form. So, this is the corresponding parameterizations. So, phi of x y is equal to this, where x comma y running over r, and this is an element in R3, right. So, given the explicit form of my surface, there the corresponding parametric representation is nothing but the phi, where phi of x y, whose first component x, second component y, and third component is small g. Again, I already discussed this part, right. Look, so this is the one. If the surface has an explicit representation, that means if I have z is equal to f of x y, then this is the corresponding parametric representation. That means first component is x, second component is y, and third component is f of x y. So, exactly thing I am doing there, right. Yeah. So, therefore, I have this component, and this is perfectly all right. Once I know my component, first component, second component, third component, then what you have to do? You just calculate what is phi x, what is phi y, what is phi x. You just take the partial derivative with respect to x variable each of the component. So, first one will give you 1, second one is I have to take the partial derivative with respect to x variable, because since y is there, so it is 0. And what about the partial derivative with respect to x variable of g? That means part del g del x. Okay. And what about phi y? Same thing. If I take the partial derivative of the first component with respect to y variable, that will give you 0, second component will give you 1, and third component gy. So, that means I have the expression of phi x, I have the expression of phi y, you just take the cross product. If I take the cross product, this is the corresponding formula, and you end up with this is the corresponding vector. So, this is component is minus gx times I cap minus gy times j cap plus 1 times k cap. So, if I take the absolute or norm, what is the square root of minus gx square minus gy square plus 1 square, that means this is square root of 1 plus gx square plus gy square. So, in that case, what is my unit normal vector n cap, which is, if I have a parametric representation, you know, plus minus phi x cross phi y divided by modulus of phi x cross phi y, which is in terms of my explicit representation g is nothing but minus gx I cap minus gy j cap plus k cap, then square root of 1 plus gx square plus gy square. So, this is the formula if I have a explicit representation of my surfaces. What is the formula for unit normal vector? And the earlier one, if I have a parametric representation of my surface, then this is the corresponding definitions of unit normal vector. Okay. So, finding a unit normal vector of a smooth surfaces. Okay. So, the first one is the parametric. If I have a parametric representation of my surfaces, then this is the corresponding formula for unit normal vector. If I have a explicit representation of my surface, then this is the corresponding formula for unit normal vector. And third one is that if my surfaces is given as a level surfaces, right. That means if I have a surface S defined by the equation g of x y z is equal to 0, that means if the set S is given by x comma y comma z, where g of x y z is equal to 0, then what is the corresponding what is called unit normal vector in this setting. So, the normal pointing outward or positive normal to the surface S is given by n cap, which is nothing but plus minus gradient of g divided by modulus of gradient of g. And what is gradient of g? Which is nothing but gx del g del x del g del y del g del z divided by square root of gx square plus gy square plus gz square. Okay. So, that means if I have a surface which is nothing but the level surfaces given by the equation g of x y z is equal to 0, then the corresponding normal pointing outward or positive normal, I should say, it's nothing but the n cap, which is plus minus. Well, I am talking about outward, means actually the only positive sign should be there. So, I am just writing this is plus minus gradient of g divided by absolute of gradient of g. What is gradient of g? This is of course the vector del g del x comma del g del y comma del g del z divided by normalize. Okay, oh, exactly. So, this is the plus sign, right. So, that is why I am saying this is the positive actually. Okay. So, that means this should not be there. Okay, this is the plus sign is given, right. So, that is why I am saying this is normal pointing outward or positive normal. I mean, this is nothing but the calculate the gradient of g, that means gx del g del x del g del y del g del z divided by just normalize it square root of gx square plus gy square plus gz square. Okay. So, this is the corresponding formula for the unit normal vector if my surface is given as a level surface as corresponding to the functions g x y z is equal to 0. Okay. So, then I have just smooth surfaces. What is the smooth surfaces mean? I say that. So, a surface is called the smooth surfaces. So, I already discussed couple of things there, extend smooth surfaces. So, this is another way. So, smooth surfaces in R3 in terms of parametric representation I have given, couple of example I have given. Then what will be the corresponding normal vector corresponding to the smooth surfaces if it has a parametric representation, if it has a explicit representation, and if it has a what is called level surfaces, that I have discussed. There is another way I can say that smooth surfaces. So, that means a surface is called smooth if it is two sided. Two sided means what? The surfaces will have two faces and I can go from one face to another face via the corner, right. So, that means without passing through the corner I cannot go from one side of the surface to another side of the surface. So, I have to go through the corner of this surfaces. Okay. That is called two sided. Like if I have a Mobius strip, it is actually one surface, one sided surface. It is not two sided. Two sided surface means what? It will have two faces, one side another side. So, it has two sides, but if I go from one side to another side I have to cross the what is called corner one or side one. Okay. So, it should be two sided. S can be parameterized. I already discussed the parameterization of surfaces, and at each point P on the surfaces the normals I just discussed what is the corresponding unit normal vector of my surfaces exist and it should be non-zero. So, this is the kind of picture I draw. So, this is the one portion of the surface and this is the another portion of the surface. It has two sided, and if I go from one side to another side I have to cross the what is called the boundary region. I have to cross the boundary one. Okay. So, in the above picture, so plus n cap of p is pointing outward, as I said positive means outward, and if I draw minus n cap of p then it will actually point it inward. Okay. So, that means this I also think about this is another way I can think about what is called smooth surfaces. So, our surfaces is called smooth surface if it is two sided. Okay, number one. Number two, it could be parameterized. Okay, it will have a parametric representations, and at each point of the surfaces S I will have outward normal and the inward normal. And what is the normal? I already discussed in my last couple of slides. Okay. So, if I have surfaces having these three properties, then I will say that these surfaces are smooth surface. Of course, I have discussed the examples of smooth surfaces like sphere, upper hemisphere, cone. These are all smooth surfaces. Okay. Okay, so I think I should stop here. So, till now I have discussed all the concepts of surfaces, couple of examples, definitions of smooth surfaces, then parametric representations, then the definitions of unit normal vectors, and then couple of surfaces if I have given like in terms of parametric form what is the corresponding formula for unit normal. If I have a explicit form of the surface, what is the corresponding unit normal vector. If I have a level surfaces of some functions, if the S is given, surface is given in terms of level surfaces, then what is the corresponding unit normal vector. Once I have all the concept, then of course I can define my smooth surfaces in this observation as well. Then it should be two sided or it should be parameterized, or at each point I have the existence of outward normal and inward normal. If the surfaces having these three properties, then I will also say that these surfaces are smooth surfaces. Couple of examples I have discussed like sphere, upper hemisphere, cone. There are many very few I have discussed. So now at least we have some idea the notions of surfaces and smooth surfaces along with uninormal vector. Now once I have that one, the concept of surfaces, now I am in a position to define what is called scalar surface integral and vector surfaces integral. I think in my next lecture I'll start with the definition of what is called scalar surfaces integral over smooth surface. Smooth surface I have already discussed, right? In R3 definition of smooth surfaces I have discussed. So once I have the notions or kind of definitions of smooth surfaces in R3, then my next plan is to talk about what is called scalar surface integral in over those smooth surfaces, and then of course I will talk about what is called vector surfaces integral over those smooth surfaces. Okay, so smooth surfaces, so this is the definitions. Okay, so smooth surfaces in R3. So this is one of the definitions, like the region R should be very nice, and this is the corresponding parametric representations, and it should satisfy a couple of properties. These are the examples, then these are the normal vector, and of course in terms of normal vector also you can think about your smooth surfaces in this way as well. It should be two-sided, it should be parametrized, and at each point P in the surfaces you have the existence of outward normal and inward normal. Okay. So now I think I should stop here. Next class, since I have the notions of smooth surfaces, then I will define the notions of what is called scalar surface integral, and couple of examples I will discuss. I think I should stop here. Thank you.